on academic writing, publishing, and career planning. Our webinars are made possible through the collaborative efforts of GRSS's technical committees and various other initiatives, bringing together a diverse community of experts to deliver high-quality learning content. During the webinar, please submit your questions through the Q&A feature, and they'll be addressed at the end. You'll be asked to complete a survey afterwards, which helps us tailor content to your interests. Be sure to check out the IEEE GRSS YouTube channel for previous webinar recordings in case you missed any. And for updates on future webinars, visit the GRSS calendar and follow us on social media. We're excited to have you with us. Let's dive in.
All right, so welcome everybody, also from my side after this small video from GRSS. Very quickly, just about myself and what kind of webinar this is. So I'm Ronnie. I'm the past chair of one of the technical committees of GRSS, namely IDF, the Image Analysis and Data Fusion Committee. And now, among other things, what I'm doing for the committee is organizing webinars, like this one. When I took over this role, I imagined to have 3 different types of webinars. The first one I called Orbit Tracks. There I invite people really at the core of what the committee is about, namely computer vision and machine learning applied to Earth observation imagery. Then the other one is a little bit the opposite of this, that I called Crosstalks, where we had the first talk a few weeks ago, where I invite people outside of our community, mainly core computer vision, machine learning people that are giving a talk about their stuff, not related to Earth observation by itself, but still really relevant and interesting to us. And then the third one, and that's where we have the webinar today, is called Earthwise, where I invite people that are more on the applied side of computer vision and Earth observation. So not necessarily academics and researchers, but more people working in industry for smaller or larger companies, or governmental agencies and so on. So I'm really happy that we have this talk today by Subit. Subit did his PhD at the University of Florida. Then he worked a little bit for Indigo Agriculture and Telos Labs for using machine learning to do crop mapping from satellite imagery. But now he is already, since quite a while actually, probably tells you a little bit more about this by himself, with Floobase, where he is the vice president for technology. And the goal of Floobase is to produce high quality maps of flood events. This kind of maps are needed by first responder, for example, flood managers, insurance companies, and so on. And for that, they are using all kind of things, well, whatever gives them the best results, but of course, including satellite imagery, both optical as well as SAR, and also a lot of deep learning. So I'm very happy to have this talk today, and I hope you enjoy it as well. There will be room for questions. You can either put them into the Q&A box if you want. If you're not shy, you can also just raise your hand at the end, and I will unmute you, and then you can ask your question directly, whatever you prefer. All right, and then without further ado, Subit, please, the floor is yours.
Great, thanks, Ronnie, and thanks for inviting me. This is sort of a different talk than what I usually give, which is more focused on the technical work that we do at Floodbase. So when Ronnie asked me to talk about, in general, how the computer vision and machine learning methods are used in industry, I thought to myself it would be a great and kind of like different thing to do a review study, but in industrial applications. And then I quickly kind of like figured out why people don't do review studies in industrial applications, which is that, all the methods are pretty opaque. But I was still interested. And so I kind of like talked to a lot of people who kind of work in this field. And I think I have like a very broad-based idea of kind of like what people and what users and scientists are looking for in this specific field. So as I'm kind of like starting my talk, which I promise is not going to go on for too long, and there's going to be a lot of time for questions. And I'm excited to kind of like talk about this field with people. I would ask you to raise your hands on Zoom if you are a student who's wants to work in this field, and keep your hands down if you already are a professional or who's in this field. Okay, so I see a few hands. Okay, great. So hopefully, what I'm going to want to come out of this talk are basically my opinions that are being derived from talking to a lot of people in industry. And if you are helpful and looking to contribute to this effort of increasing societal resilience to physical climate risk, these might be useful for your work, kind of like with response agencies, policy agencies, financial and insurance companies that make up this sector. These kind of trends and opinions might be completely different when we are talking about other sectors, because I have not talked to scientists and researchers in other sectors. There are some adjacent sectors which I'm going to kind of like, briefly cover. And then also, this is not about Floodbase or the research at Floodbase. If you are interested in the research at Floodbase, you're welcome to ask me questions. There is one slide about Floodbase because it is, doing a lot of insurance. But in general, this is about kind of like broader industry trends. Okay, so without further ado, let's talk about physical risk because, it's in the title of the webinar. This framework for thinking about the societal risks caused due to climate change is from the IPCC, the Intergovernmental Panel on Climate Change. And in general, the outcome is the kind of like adaptation or mitigation to physical risk and transition risk. So, on the left, we have these societal assets. So we have lives and livelihoods. We have key infrastructure, and then we have financial assets. So infrastructural assets include, the house that you're currently joining the webinar from, universities, industry buildings, bridges, roads, and financial assets are not as tangible as infrastructural assets, but still, very real. So these are mortgages that you use to, buy your house or start a business. They're kind of insurance products that cover your belongings if there's a wildfire. And all of these societal assets are exposed to two different kinds of risk from climate change. The first one, which I will be focusing on, for the next few minutes, is physical risk, which is basically the risk caused by physical hazards like extreme heat, extreme cold, material degradation, and then also, like acute hazardous events like tropical cyclones, coastal flooding, wildfires, and other effects of climate change. Then there's the other kind of risk, which is called as transition risk, which I won't be covering as much in detail, but is also real and is, also due to climate change, which is basically the cost of moving away from fossil fuels and a carbon-rich world. So an example of that would be, if we run out of fossil fuels, basically we will need a lot more electric vehicles than what we have right now. And that is a risk and that has a cost. And the IPCC calls that transition risk. Transition risk also covers things like carbon credits, which is a way to pay for transition risk. We will cover it briefly in some of the examples that I'm going to show you, but in general, I will limit myself to talking about the ways in which deep learning, remote sensing, and computer vision methods are being used by industry to respond to physical risk. So the first part of this talk will be basically looking at an interesting product that is across the value chain. So that basically goes all the way from Earth observation to the adaptation or mitigation that we want from physical risk, and identify kind of like the key properties of like what makes a good product, and what are users looking for. Then in the second part of the talk, I will talk about some very interesting examples of how machine learning, computer vision, and Earth observation are used to address physical risk, and like go into each of those kind of like at a very superficial level, but hopefully enough to give people who are interested in this field an understanding of kind of like what the industrial landscape looks like. And then in the third part, talk about some of the computer vision techniques that, based on my survey of the physical risk response industry, people are using, and then also people are the most excited about. And yeah, if there's any questions, please put them in the chat, and I will either kind of like address them as I go on, or respond to them at the end of the webinar. And especially if you have questions about the IPCC framework for thinking about climate risk, because it's very important and it's going to be basically the focus for the next hour, please let me know in the chat. Okay, so as promised, here is the Environmental Hazard Adaptation Atlas that was released actually just yesterday by Stanford University. And I think it's a very good example of kind of like what a physical risk product looks like from the policy user perspective. So I'll play it again, but basically what this video shows is the smoke-related mortality and how it changes from 2010 to the last 5 years. And you can see kind of like clearly there's like some trends that they detect. Basically, the smoke-related mortality caused due to PM 2.5 concentration and wildfire smoke used to be more on the kind of like northern border of the US and Canada. And then in 2010, and now it's actually kind of like focused on kind of California, Nevada, and this area. And the reason why I think that the Environmental Hazard Adaptation Atlas is really cool is because it kind of coalesces research that has been going on in a lot of interdisciplinary fields over the last decade or even longer to kind of like present an insight that is actually useful for policymakers. So on the kind of like, I try to kind of categorize the research into like more on the data side as more on the insight side, but obviously it's a spectrum, and any classification of this nature is imperfect. But like you can think of the raw data side as being, the folks who developed the Collection 6 multi-angle atmospheric correction algorithm that basically, develop some of the aerosol detection methods that feeds into the model. We have the ERA5 ECMWF climate records that are used to as part of the model. And then, about a decade ago, we had the MERA simulation framework, which is used to make sure that like a lot of the product here is gap free. And then we have kind of like farther more research into on the analysis side. So some ensemble-based deep learning methods to make sure that we can kind of like assign causality to the effects that we are seeing. And then the effects themselves, which is like the long-term mortality trends that are associated to black carbon and PM 2.5. So basically, like it took all of this to provide this product, and we can kind of like see that in the extreme heat case as well. So this shows the extreme heat days, which is a temperature, which is the annual count of days where the temperature is above 35 Celsius. Also, because of climate change, this has increased more and more in the last 20 years. And then because of the extreme heat days, they show the mortality on extreme heat days. So this is basically, you know, the increase in deaths on a day where the maximum temperature is more than 35 Celsius. And then this is like the actual insight, which is what are kind of like the changes in exposure, health outcomes that are a result of providing people with general weather forecasts, with extreme temperature action plans, with energy efficiency programs. So this is when I was talking about at the beginning, the kind of like impact. This is the impact that we want to kind of like see as a result of efforts in this industry. So we want to go all the way from the Earth imagery, which is MODIS, and then go to this kind of analysis, which is, you know, if we have an energy efficiency program in a sensor tract somewhere, how does that affect the kind of like health outcomes or realized exposure to a physical hazard? So hopefully with this kind of like really cross-cutting example, it's clear that we actually kind of like need to think about each part of the value chain. And I think that is kind of like the fundamental lesson that I have learned in industry, and that I hope, you know, everyone kind of like can empathize with, which is that you have to kind of like think of the user of like what you're producing, and you have to think of their users and their users all the way until you have something like this, which is a kind of like insight that can then be used to increase societal resilience to physical risk. All right. What do these users need? So this is again from a survey that I did with a lot of people across the value chain in the physical risk space. So number one is trust and transparency. So the users of the data need to trust and understand the quality and provenance of data. So quality is, you know, basically like how good the data is and how correlated it is to your stated purpose. And provenance is where it's coming from. So you need to kind of like understand both of these things to, you know, use the data. The second thing, which is kind of, you know, a little bit in conflict with the first thing, is technical abstraction. So the users of the data want to be sufficiently abstracted from the details of how the data was made. So if you are an insurance user of Earth data, you really don't want to be thinking about atmospheric correction and incidence angles. These are kind of details that should be decided for you by the people producing the data. And this results in some conflict with the trust and transparency portion because, you know, if you don't understand every detail of how the data is made, maybe you don't trust the data. And this is where societies like IEEE GRSS come into the picture because they can basically provide some strong guarantees of trust and transparency, while at the same time enabling technical abstraction in the data products. And the third thing, which is wrong on the slide for some reason, but is cost effectiveness, which is basically the data needs to be cost effective and produced at a cost that can be paid by industry. Because In industry, we usually don't really get free data, except for from government agencies, but they usually come with some licensing cost or some cost to acquire. And while everyone has a cost to produce the data, if the cost to acquire is too high, then the people who are kind of like the users of the data just don't use the data, and that's kind of like the physical reality of the world we live in. So basically, we need to kind of optimize all of the things: trust, sufficient technical abstraction, and cost effectiveness, to make sure that a data set, a data layer, or a method is seeing use in the industry. All right, so in the second part, I'm going to just show some examples of the use of computer vision, geoscience, and deep learning in industry for physical risk. So this is a very pertinent example. This is called Climate Trace. So Climate Trace basically measures emissions in different parts of the world using computer vision and satellite imagery. And then what they do is they kind of work with the industries to mitigate the emissions when they're produced, and thus kind of reduce physical risk. And what they do is they take satellite imagery. They take some medium resolution satellite imagery like Sentinel, and they take kind of different spectral components of that satellite imagery. They also take some high resolution satellite imagery. And then they use deep learning to classify human activity. So they also classify kind of like some parameters of the human activity. So for example, they might look at satellite imagery and use a deep learning classifier to detect that there is a power plant operating there. Then they also use AI to detect the kind of like capacity at which the power plant is operating, maybe by looking at some high resolution imagery. Then they have kind of like sector-specific models to estimate emissions. So for taking our power plant example, they have some models that convert the plant's fuel type and the operating capacity as determined by deep learning, and then convert it to carbon emissions. Then at some locations, they have ground truth observation data available to kind of like check these predictions. And then they have kind of like some ensemble methods that spatially fills in the estimates and adds uncertainty. So that they can tell you, for example, this is the state in India that my parents live in right now. And there you have kind of like, in 2024, this much carbon dioxide emitted. And they also, because of kind of like the sector specific models and deep learning methods used to identify activity, they divide the emissions based on different sectors. The second thing that I wanted to kind of like talk about is nighttime lights, which is being used a lot right now in the physical risk space. And basically, there's kind of like some themes of how it's used. One is to kind of identify different regimes in urban change. So on the left, you see nighttime lights over a Yemeni city. And there was a very widespread grid failure due to a terrorist attack. And they basically use the nighttime lights to detect kind of recovery from that grid failure, which is really important in the financial industry when you're thinking about measuring kind of like productivity and measuring economic resilience in different parts of the world, especially in places where you don't have trusted good data sets. And this theme continues on the project that you see on the right, which is kind of like machine learning analytical framework to project future nighttime lights using kind of like the IPCC emissions pathways. So what they do is they look at the different emissions pathways that are provided by the IPCC. So these are numbered on the right here and called SSPs. And they basically kind of project urban area and carbon dioxide emissions from the nighttime lights intensities that they see in the history, and then interpolate it using SSP scenarios, which is the kind of analysis that a lot of financial modeling firms do these days to kind of try and understand the future impacts of climate risk. The kind of like next interesting application of nighttime lights is credit scoring, and this is a little controversial, but in countries where you have very little data available, especially in rural areas, which is, China, India, credit scoring in those areas can be really difficult. And what a lot of financial firms and kind of, insurance agencies are working on is using things like nighttime lights to essentially derive a surrogate credit score that can be used if your kind of, other data that you use to estimate credit scores is not enough. And this is one of the papers that is cited by lots of folks in the financial industry as being kind of like the first real study that takes spatial remote sensing imagery, including nighttime lights, population distribution, land use, water use, and basically creates a credit score based on the economic activity and the and the growth seen in a particular area. So yeah, nighttime lights, very interesting data set used across the physical risk industry. And I think that there's a lot more potential uses here that we are kind of like just getting started looking at. So if you are interested in the physical risk space, interesting uses of nighttime lights is a very good area to focus on. Okay, coming to insurance and reinsurance applications. So because I work at Floodbase, this is a part of the industry that I'm personally very familiar with. This is an example of the use of deep learning for loss and risk estimation. So basically, this company, Nearmap, what they do is they look at satellite imagery and estimate, number one, how susceptible it is to physical risk due to a particular hazard. So you can see they say, wildfire hazard potential. The vegetation cover is also contributing to wildfire hazard potential. And then they also have deep learning classification techniques to see, like what the roof condition is, which is going to basically factor into, how much loss it's going to incur if there is a physical hazard. And having this done using satellite imagery is very useful, because that means that if, the kind of like adjustment process, if there is a wildfire or if there is a cyclone, is going to be much easier. And these folks out here at 2223 Auburn Avenue, USA, are going to potentially get paid their claim way faster than if they had to actually kind of like send a physical adjuster to their house. And that kind of trend of faster adjustment process is key in parametric insurance as well. So on the left, this is kind of a Liberty Mutual US technique for paying out when there is a wildfire. So they basically combine some satellite imagery and vegetation indexes. They have a fire severity processor that is based on machine learning. And then they create custom indexes that are used to pay out when there is a wildfire. So for these parametric insurance applications, there is no adjustment at all, which is kind of a typical step you have in an insurance policy, but you just use Earth observation and some machine learning algorithms to calculate an index, and your insurance payout is completely dependent on the index. So you can get paid out immediately when there is a loss event. On the right, you see another big reinsurance company's crop insurance scheme. So basically, if you are a farmer and you're planting a crop, you get paid out if your crop yield is less than some threshold value, and you don't have to, again, incur the time cost of adjustment. And then the last one, which I'll talk the least about, is flood-based. So we do parametric insurance for floods. This is at a country scale. So we use MODIS and VIIRS imagery for this scheme to basically map floods all over Colombia. And we also use some custom deep learning frameworks to estimate flooding. And if the flood exceeds a threshold, the policyholders in Colombia can get paid out without having to have a loss adjuster visit their property or anything like that. Okay, so in the third part, we'll talk about the techniques that we kind of did not really talk about when we were talking about the financial credit monitoring and insurance applications that deep learning and computer vision are used for. Excuse me. The first really interesting thing that I found out when I talked to, most people in this field is that if you have a geospatial inference problem, you almost always just use random forest, which was, very surprising to me, but it kind of like tells you how powerful this methodology is and how much people trust it. Whenever there is some sort of a inference situation in most companies, I think the first thing, and maybe the only thing that is used is just like a plain old random forest. But if you have some sort of a, spatial correlation in the inference problem that you're looking at, which is true for almost all the examples that we saw in the last section, usually random forests by themselves are not enough. And then I think once you move on from that, most people just use units. This is kind of like a very established method in the GeoAI, especially in the physical risk field. Almost all the examples that I showed in the last section actually, use UNets as the way that they do geospatial inference. There are very kind of key advantages. It generalizes very well in a huge diversity of applications. It is very cost effective to retrain. Like there is some initial cost to adopting a unit that you typically don't have with, gradient boosted trees or random forest. But once you incur that initial cost, it's actually pretty cost effective to maintain it or retrain it. And then you have kind of like a lot of different studies that use units for GeoAI applications in the last however many years. So people really have this like trust components that I talked about in the first part of the webinar as being one of the kind of like 3 key things that users are looking for. So I think like at this point, if you take random forests and units, you probably have coverage over 95% of the physical risk industry. If you talk to most people, this is what they use. And anything that comes after this is kind of, being slowly adopted. I don't think is going to be widespread anytime soon, but I will cover just to make sure that we have a complete overview of the methodologies used. If you decide to do something more I guess, advanced than use a UNet, it is because having spatiospectrotemporal inference using UNets, you probably need like 4D convolutions, is very messy. And then usually UNets are sensor specific, though not always. Incorporating multimodality and multiple sensors in a UNet can be, at the very least, very messy. So if you decide to not use a UNet, I would guess that like these two are kind of like the major issues. And then what you do is use vision transformer. So there is some early adoption. I would say that if you are looking to go beyond UNets, transformers or self-attention is now clearly the dominant method based on kind of like all the conversations and reviews that I did. I think conval STM's not used as much because people say that they're like pretty difficult to train. I have my kind of like hypothesis on why this is for satellite imagery, but like in general, for other geospan, for kind of like dense spatiotemporal dump problems within geoscience, like stream flow prediction is a good example. Conval STMs are still kind of like the dominant way in which this is used in the industry. Did not really go into that because it doesn't use satellite imagery and because it's, kind of like not related to remote sensing. But for example, if you're in the US, you will see that your power prices change all the time. And your power prices are, if you're in a hydroelectric area, are linked to basically how fast the river is flowing. And all of those kind of like predictions and pricing is probably done by a conval STM. But in satellite time series, we usually don't have good local temporal structure in the data. So conval STM's pretty hard to train. And I think transformers and self-attention are basically the dominant method. The upfront costs of using transformers is pretty high compared to a UNet. But in some cases, as reported by the early adopters, the advantages can outweigh the costs. And then for my last slide, I just wanted to mention foundation models. So foundation models are just basically kind of like some vision transformers that have been pre-trained using self-supervised learning over a large corpus of data. And these are definitely, if you talk to people, these are what people talk about the most. Because as as in contrast to using a transformer and figuring that out by yourself, having a pre-trained foundation model is a much lower barrier to entry, especially if you're in the industry and you don't have a lot of time to spend on a particular problem. On the top, you see the Prithvi Foundation model, and on the bottom, you see the Terramind Foundation model by the same authors at IBM. At the kind of like current generation of foundation models incorporate multimodality natively, which is very exciting for people in industry, because then you don't have to depend on whether there is a Sentinel-1 image over your region. You can use other satellites, which is what everyone has been looking for. I will say though that everyone that I spoke to basically said that the performance of a fine-tuned foundation model does not exceed custom trained UNets. So if people have a custom trained UNets, they are holding on to those at least for now. Maybe as kind of like they get better and there's more adoption, that will change. But right now, the kind of like cost benefit analysis of using foundation models is still not reached the point where it's seeing a lot of adoption in industry. And then the last thing is embeddings. So embeddings is just, if you just use the encoder of these foundation models, and then you do some transformation on it, sometimes you get the embeddings. And we have kind of really interesting sets of embeddings being released by big companies right now. So Google released Alpha Earth Foundations. There's the Clay Foundation model, which was developed by Clay and DevSeed. And then there's an open source embeddings data set called Tessera that was released recently. And then the promise of these data sets is that you can use them as features without really thinking a lot about how the features were generated. And they're going to be broadly useful across different sectors, not just physical risk, but like different sectors of the industry. And people in physical risk are very interested in exploring these because they provide a way to compress geospatial information and make it usable in a lot of downstream models. But there are kind of like hesitations around the three things that I talked about: trust, transparency, and cost. Um, I wouldn't say that these embeddings are trusted yet. They will need a lot more kind of like study by researchers and other folks because before they're trusted. There is essentially no transparency because for a lot of these models, the kind of like encoders and the models themselves are not released or open source, and just the embeddings are released, and that results in kind of like there being some loss of transparency. And the cost is also a lot. If you use Alpha Foundation embeddings for as an example, you have to use Google's platform, and that can be pretty expensive. So I wanted to end the talk by saying that foundation models are kind of the next big thing, and embeddings promise a way to really change how geospatial inference is done in the physical risk space. But it's still not used widespread, and I don't think it will be until the trust, transparency, and cost issues are addressed. But it's a very exciting future for those of you who want to work in this space. And if you do, I'm always available for questions, consultations, whatever you want. Thank you.
Yeah, thank you, Subit. That was excellent talk. I learned a lot, right? I mean, the latter part I knew a little bit. We have discussed it a
Yeah.
few times already, but the first
Yeah.
part was quite interesting. There's already one question in the chat that I can read to you. In the meanwhile, I hope some others are also thinking about what they still want to know. So the question in the chat was whether you can recommend any alternatives to explainable AI regarding monitoring heterogeneous effects of climate risk, and whether you can provide some information about causal inference-based loss estimation.
Yeah, great question. I would say that like in terms of explainable AI alternatives, um, there's been a lot of kind of like work done in the literature about how to use or how to kind of like use frameworks like vision transformers and UNets, and then investigating causal effects of features within those. I would suggest kind of like those frameworks instead of trying to, invent your own. And that's probably a good starting point. In terms of causal inference-based loss estimation, there's like a whole industry that does loss estimation based on causal inference. Unfortunately, most of those methods are not open source. But I know that, for example, FEMA in the US has some loss estimation based on CAT models that they provide openly for some perils, for perils that they classify as, I guess, like, the primary perils. But they're only available for the US, unfortunately. So the best way, if you're not looking for primary perils in the US, the best way would be to kind of try and collaborate with some insurance companies who usually have these causal inference based models. Um, and like most kind of researchers at insurance companies would probably like to collaborate with people. So that's a good place to start.
Great. Lakshmikant, I hope that answers your question. And then we have a second question from Mohammed, who asked whether you have any recommendation on how best to utilize satellite meteorological and soil data for analyzing crops of cultivated within specific ecological zones.
Yeah, again, very good question. So I would say that, I would ask if you're doing a general risk analysis of crops or if you're looking for a particular kind of risk. Usually I would say, depends on if it's a general risk, then it's kind of difficult because it is very particular to the region that you're looking at. Risks in Southeast Asia look very different from risks in South America, look very different from risks in the Corn Belt in the US. So the satellites, weather and soil data that you would use for the different parts of the world would be completely different. If you want a completely generalizable answer, I would say maybe utilize some of the foundation models that use satellite meteorological and soil data. Maybe see if the embeddings make sense. And even if they don't work, I think that would be a very interesting thing to find out and publish about, because that will show people that something is missing. So yeah, maybe like if you want to completely generate generic answer, I would recommend using some embeddings data or foundation models that incorporate satellite, climate, and soil.
In the first part of your talk, you covered like different types of risks. Do you have a feeling that like a particular group of risks is missing from that, where you can't really exploit satellite imagery or observation data, and maybe why this is missing or whether this will change in the near future?
Yeah, so one of the kind of blind spots is that the IPCC framework is forward-looking. So satellite data is only about kind of like the historical record and what we know right now. So the forward-looking part is pretty difficult to estimate just by using satellite data. So that's a pretty clear blind spot. You'll see that some of the studies that I showed use basically SSP pathways to do the forward look. So they kind of like have some intermediate non-satellite layer that they estimate, and then they try to interpolate that forward using pathways, climate pathways. But that's kind of like the biggest, most obvious example. And then there's like other risks that are completely I mean, satellite data cannot be used at all. So a lot of the transition risks, for example, about carbon credits issuance and stuff like those risks are usually very opaque. And until we have I don't know, like high resolution airborne imagery everywhere, I don't think we can use remote sensing very easily.
I see. Okay, I don't see any other questions and also no raised hands, so I would like to close with one of my questions, which is a little more, let's say, general, not necessarily connected to your talk. So you're working in industry already since quite a while, and I'm purely academic. And what I'm noticing is that many researchers need to balance between like short-term applied results that are like a little bit more important in industry, but also become more important in academics because you need to publish a lot of papers, and for that you always need to be on the top of the leaderboard. So on the one hand, we have this like short-term results, and the other one is long-term fundamental questions. So really, generating knowledge for the next 10 years. So how do you personally balance between those two things in your work?
So It's also kind of like a question of where in the industry you're sitting. I work at a company with 25 people, so we have to kind of like leave the long-term knowledge generation to kind of like, academics and larger companies like Google. And what we do is we take those kind of like, a lot of the good work that's been done by academics and other parts of the industry in the long-term knowledge generation, and then we apply it to, smaller problems in the short term. The way in which it's different from publishing the next paper is that the generalization requirements especially for what we do, but I know this is true for like the whole physical risk space. The generalization requirements are very high. So a lot of the times what we see is when we look at some papers that have been released, we try to implement those methods and we find that it's like, overfitted to like a particular geography and a particular, uh, let's say, modality. And then when we try to generalize it, it doesn't work well at all. This is why I think that like most people use random forests and, now I think most people use units, which is that their generalizability, if you train them well, is super high. So that's kind of like the barrier that I think that most academics have to pass, which is, even if you're not doing, let's say, like knowledge discovery that is going to last for the next 10 years, I think like paying more attention to whether the research you're doing is generalizable, even if it's not, like looking into why that is, I think that is going to be super useful when you're transitioning into industry, because that's the kind of questions we ask ourselves all the time, which is like, okay, I have this methodology that's maybe working well, and then it's not working well. So how can I make it work well? And that is very different from developing a new framework that is publishable.
So what would you say if, let's say, a new PhD or maybe even a postdoc wants to enter this field of physical
Mhm.
risk assessment? What kind of mindset or skill set should this person bring?
I think very, very deep understanding of simple methods. So, you don't need to understand how like a kind of like very complicated diffusion model works, but you should be able to really identify patterns and things that you see in a UNet inference, and be able to kind of understand how causality works within the UNet framework. Like, how can you investigate causality? That's one thing. And the other thing is just like being able to speak in an interdisciplinary language. Um, Most of the research that I came across when I was doing this like industrial review was extremely interdisciplinary in nature. And the scientists that I talked to could really kind of like, speak about CV and Earth observation, but they could also speak about kind of like economic modeling, and they could also speak about like what users want to do. They could speak in their users' language. So I think like obviously like you don't know who your user is going to be before you're in industry, but being able to kind of like speak in different languages based on who you're talking to, I think is a skill that you can learn in your PhD by going to talks outside of your group, your field, your university. And there's many opportunities for that these days because a lot of the public agencies actually, collaborate deeply with academics. So just kind of like maybe, instead of doing another conference talk at a computer vision conference, consider doing it in one of the local kind of like UN meetings or something like that. And that will teach you how to communicate what you're doing to a group of people who uh, care about uh, the data you're providing, but don't necessarily care about each technical detail.
Yeah, great. Thank you. All right, no other questions from the audience. I hope everybody enjoyed it. I certainly did. Thanks again for being here, Subit. And thanks also for everybody in the audience for being here and engaging and paying attention. The next webinar will be from the orbit tracks, which is scheduled for October 9th. So just stay tuned. I think the details are already online. You saw the QR code before, so maybe we see each other there again. Right. Thanks again, Subit, and see you around.
Great. Thank you so much, Ronnie. Thanks, everyone.